but it doesn't need to be over the whole domain, right? Here I
I
have
see.
these initial boundary conditions that are trained on supervision, and then everything else in this interior of the domain is trained with self-supervised loss by penalizing the residual of the PD constraint.
Are you running some sort of cherry picking while you're populating these Ys from the solution space? Or is it a random set of Ys that would be not the entire set, but a subset that is randomly chosen
Yes,
for training?
good question. So it's very, very good question. So there is these temporal and spatial coordinates, these blue points, that are sampled in vanilla approach randomly, let's say from uniform or Gaussian distribution. And this works for simple problems, but when you have stiff systems, when there is equations that develop shocks like Burger's equation, you want to sample more densely in those regions where those shocks or stiffness is manifested. And more adaptive sampling is warranted here. And there are interesting papers that are providing different sampling strategies for these physics-informed neural networks to converge better, because they are known to be ill-conditioned problems. So there is a lot of tricks that in practice you need to do to actually solve complex higher dimensional PDEs, including adaptive tuning of penalty weights when you have these multiple terms. I'm not showing them here, but that's what in practice you would have to do.
Right,
Jen,
thank you.
I'm sorry.
Thank you. I just said thank you.
Okay. Jan, I have also one question. People from physics or fluid community, they apply proper orthogonal decomposition model reduction techniques to PDs, and then they use such models. So, for example, just as a proposal, is it possible, for example, to first apply the same methodology to obtain the reduced order model, and then replace the PD domain with the reduced order model, and then use that one? Because in this case, probably the computation wise, it will be better. So are there such approaches? Instead of the PD domain, you first apply a model reduction technique like proper orthogonal decomposition, and then you use the same procedure.
There are some approaches that deal with learning the physics in the latent space, and I will go over those later. But I'm not aware of any physics-informed approach in the latent space, because now you have a problem of representing your physics equation in the latent representation, right?
Okay.
So that exactly I'm not aware of.
Okay.
The good news about these pins that they are not very expensive to train, because what you're doing in a forward evaluation, you are evaluating the neural network forward in time and PD forward in time in computing these partial derivatives. And then you are having this empirical risk minimization loss. That is just a weighted sum of terms over many batches. And then you're computing the gradients of those using automatic differentiation. So you don't need to run full solution of the PD forward in time in pins. That's the whole advantage. You don't run finite element method. The second method that I want to talk about is so-called learning to optimize, that has been used in operational research community in great success in power systems optimization and in supply chain optimization. So these are the primary application areas, but is really heavily rooted in OR theories. But when you look closely about the methodology itself, you can say, oh, well, this resembles physics-informed neural networks for PDs. So how it is so? Well, we start with sampled parametric scenarios that can represent uncertainties or different cost vectors in your linear objective or different constraint vectors. And they can be sampled as a distribution. And they are features to neural network that now represents the solver that returns the primal solutions sometimes primals and duals together, but very often just primal solution to the constraint optimization problem that is given by known objective and known constraints. And now, because we are dealing with systems that are requiring hard constraint satisfaction, very often we embed these optimization problems inside. So if G and F, your objective and constraints, are differentiable, you can embed them as layers in your computation graph. And now, in a physics informed or domain ever loss function, you can do the same trick that we are doing in pins. We are doing empirical risk minimization on minimizing your objective function and penalties of constraint violations. In this case, I'm showing inequality constraints only, but you can treat this with equalities as well. So what is this? Well, this is nothing else as a penalty reformulation of the constraint optimization problem and solving it with stochastic gradient descent. There are extensions where you can train this with penalty barrier methods, or you can train this with augmented Lagrangian, but these are, again, just different modifications of the same idea. And because we want to have hard constraint, very often we also deal with so-called feasibility restoration layers or feasibility repair layers that are implemented as differentiable projections. And depending on the constraint set, this differentiable projection can be closed form, like on box constraints, or it can be gradient-based, like projected gradient method, or if you have more complicated feasibility domain, like this is a convex set, you probably need to solve optimization problem in the layer. And then you would need to differentiate through convex optimization program. So these are all techniques that are being used in learning to optimize. But my argument here is that underlying idea, when you abstract them into these four major components, is very similar to pins, right? Start with collocation points, replace the numerical solver, your Gurobi, your integral point, with neural solver that will give you approximate solutions, and now use your domain ever layers, in this case, the objectives and constraints, to guide the training of this neural network in self-supervised setting through the penalty method over distribution of scenarios. Is there any question here? If not, I will move to learning to model dynamical systems with neural operators and neural differential equations that is becoming very, very popular. And here, instead of sampling collocation points or parametric scenarios for static problems in the sense of optimization, now we have dynamical system constraints. Now we have time series data that we want to match with our system dynamics model. So this time series data typically can come from single rollout trajectory or multiple rollouts, but we typically discretize the measurements. We have finite horizon length of those, and we have m number of those. So this is our training data set, batches of trajectories. And now this is a realm of traditional system identification. In traditional sys-ID, you would probably do linear state space models and try to estimate your ABC matrices to fit this linear model to your time series data. Or you would do dynamic mode decomposition, proper orthogonal decomposition, as Erkan, you mentioned, to obtain the Koopman model representation. So what we're talking about here is nothing else, just extension of the classical system identification to handle nonlinearities, very often approximated by deep neural networks. So one popular approach is deep or neural ordinary differential equations that want to model differential equation, but we don't know the differential equation. So on the right-hand side, we use neural network to represent your x dot equals f of x. So, okay, now I have neural network that represents my vector field of the ODE. In order to differentiate through that, because this is a continuous time model, I need to discretize it. I need to have ODE solver. So you choose some form of time stepper as a layer in the computational graph. So that's your domain-aware layer. And this time stepper can be Euler discretization or Runge-Kutta solver that now we need to compute sensitivities through. Well, there are two ways how to do that. You can either unroll the operations of your ODE solver and use backpropagation through time, basically running autograd on your computational graph, or use adjoint sensitivity method to get the sensitivities backward in time. Other examples can involve like deep Koopman operator, where in extended dynamic mode decomposition, you need to come with a library of terms, of nonlinear terms that represent your basis functions. And then you learn the linear fit in the latent space. Well, what if you don't know those basis functions? Well, you can represent them with neural networks that take your observables, lift them into latent space, then you train linear operator in your latent space, evolve the dynamics in latent space, and project back to your observables again through another neural network. So this is encoder-decoder setting. And this idea generalizes to like neural state space models or gray box modeling approaches, where maybe you know something about your differential equation. You know the structure, you want to exploit some properties, so you can do this systematically now by combining machine learning components with structural components. And the loss function now is, again, empirical risk minimization over finite horizon rollouts of your model dynamics that needs to match the example trajectories. So this is traditional residual loss training. You can add additional terms like these finite differences or other penalties on stability regularization. So there is a lot of terms that can come into play in system identification. Is there any question here? I'm going high level, so we can get the big picture, but I'm happy to follow up in each specific details afterwards. Okay, so I went through PINs, physics-informed neural networks for differential equations as neural solvers. I went through learning to optimize as neural solvers for constraint optimization problems. And I went through learning to model as neural surrogates for dynamical systems. So last category of methods in scientific machine learning toolkit I want to talk about today is learning to control, that come in principle in many flavors, but from the control theoretic perspective today, I want to focus on supervised learning to control that we call approximate model predictive control, and self-supervised learning to control that I call differentiable predictive control. So in in supervised setting, in approximate MPC, we start with solving a bunch of MPC problems. Yeah, we know the problem formulation, we know the cost function, the stage cost, the terminal penalty, we have the system dynamics, we have the constraints. We formulate our optimal control problem to solve it over sequence of control actions over finite horizon using your familiar tool, whether it's Pyom or Casadi or DoMPC, and solve it with interior point or Gurobi or other solver that matches the problem. And this is a parametric optimization problem because its solution depends on the input parameter, which are in our initial conditions, and potentially can include additional parameters like different reference trajectories or different constraint parameterizations. And with time varying parameters, we need to solve this repeatedly online. And this is expensive. So really the motivation here behind approximate MPC is to let's construct neural policy approximation of this implicit policy that is represented by optimization solver. We can do it in supervised setting by solving a bunch of MPC problems, constructing label data set of state or parametric scenarios to control actions, and then run standard supervised machine learning to get my neural network to approximate the model predictive control. But there are two problems associated with this. The first one is the data generation is expensive. In order to have good coverage of the state space, you need to solve a lot of MPC problems, a lot of optimization. Problem number two is it's hard to integrate constraints into supervised learning. So guarantees are typically done as a post-processing or verification of these learn trajectories. So,
John, I have one question.
yes.
So if I'm not wrong, I think your proposal using neural network to approximate MPC is kind of explicit nonlinear model predictive control, right?
Exactly. So explicit MPC is a wonderful idea, but in its analytical solution approach, it doesn't scale.
Yeah, but as we all know, in explicit MPC, one of the main problems is the course of dimensionality. So how do you handle this issue in your methods?
Yes, so the curse of dimensionality in explicit MPC comes from your number of decision variables and number of constraints. And the reason is because you are using multi-parametric programming to factorize your KKT system. And then in order to construct the polytopic or piecewise affine control feedback law, you are extensively enumerating all possible combination of active constraints. So these grow exponentially with the problem size. We don't do any such thing here. We are saying, forget about our KKT system, forget about enumerating all the active constraints. That will never scale. Let's do supervised learning, or what is called imitation learning or behavioral cloning in machine learning community, to imitate the MPC solution. So on a bunch of initial conditions, let's say 10,000 initial conditions, I need to solve 10,000 MPC problems. And then I'm going to use this data to supervise my neural network to provide me with approximate explicit control policy. So pure machine learning data-driven approach here.
Okay, thank you very much.
Yes, but still, yeah, the data generation is expensive. It's expensive, but not as expensive as explicit MPC through multi-parametric programming. So what can be even less expensive, my argument is, why do we do it in supervision? Why don't we do it in self-supervised setting in approximate way? So the idea is called differential predictive control. I have been working on this for like last 5-6 years, and we are starting with sampling the parametric scenarios. The same like we do in pins, same like we do in learning to optimize, and approximate MPC. So these can represent my collocation points in control parametric space, like initial conditions, or additional problem parameterizations that can represent different constraints or even different system dynamics models. So now I will represent my control law as a neural policy. So this will be my neural network. It will take the states and additional control parameters and give me control action. And now I will take that action and plug it in the dynamical system. That can be state space model, or in this case, I have this ODE system here, where F can be known, white box physics-based differential equation, or it can be your neural ODE that was trained in a step number 1 in system ID step. And what you are constructing here is basically closed loop dynamical system that you are evaluating over distribution of parametric scenarios and initial conditions. And now you are obtaining trajectories over finite horizon because we are doing these multiple rollouts over n steps forward in time. And this allows us to compute the stage cost and the penalties on each stage of the horizon, and do this empirical risk minimization training the same way like we do in learning to optimize and pins. So to make it a little bit more clear, I will go now step by step into each component. And what is really the underlying idea is to represent model predictive control as a computational graph in deep learning. Instead of optimizer like Gurobi or in Imperial Point, we are going to take neural network as our solver, as our policy representation. Or in reinforcement learning setting, this will be our actor. Then in order to train the actor, you need a critic. Well, we don't want to train the critic like in deep neural network in black box, because we know the system dynamics models, and we know the stage cause and penalty constraints for our problem formulation. So we can represent this as this closed loop recursion. I have closed loop system, takes in state, control parameters, generates control inputs. The control inputs feed into the system dynamics, it generates next state, and I can evaluate the stage cost penalties at each time step horizon and do this recursion. Now, assuming that all of these terms are differentiable or differentiable almost everywhere, I can compute sensitivities of this program with automatic differentiation. So how do you do that? Well, now represent these A, B, P, and G terms as Jacobians of my system dynamics and control policy. Well, in automatic differentiation, we can do forward or reverse mode. Here I'm showing reverse mode automatic differentiation, or so-called backpropagation in deep learning. And you start with defining your terminal sensitivity. That is typically partial derivative of the terminal cost. And you backpropagate this sensitivity backward in time through this recursion, where I have these sensitivities of the cost with respect to my system dynamic states and with respect to control inputs. And they are backpropagated through these Jacobians, yeah? And now you would ask, oh, but computing these Jacobians must be expensive. Well, that's the beauty of automatic differentiation, that we are never really explicitly constructing these Jacobians in practice. We are computing something that is called the Jacobian vector products that evaluates this matrix vector multiplication without explicitly constructing the Jacobians. So that's like really exactly. And that's what is allowing you to compute these sensitivities that you can now aggregate for computing what you can consider your critic for training the policy. Yeah. Now, taking the gradient of this loss function that is fully model-based, fully MPC inspired, in the direction of your policy parameters, you can have direct policy optimization in this way. And because everything is differentiable, everything is trainable in principle. Yeah. Now I'm showing how to train this control policy, but you can tune jointly policy and system dynamics models, or you can learn constraints from data. There are a lot of extensions that are being allowed in differential programming. So the overall training algorithm can be summarized in this setting where you define your prediction horizon, what is your batch size, because we are typically training with mini batching. What are your distributions of your initial conditions and additional parametric scenarios? You need to have the dynamical system model, either state space or differential equation that is differentiable almost everywhere, and you have some control policy representation. Typically, we are using deep neural networks, but this can be really any differentiable representation like polynomial basis functions. And what we are doing is, like in training, we are selecting the mini batches. So it's basically a B number of samples from our overall training data. And for each of these sampled scenarios, we are doing forward simulation rollout with my closed loop system and known objectives and constraints to accumulate the cost over this finite horizon. And over this mini batch, I'm averaging the cost and now computing the sensitivities using the backpropagation through time, the backward paths that I showed on the slide before. And this enables me to use gradient-based optimizers like ADAM, ADAMW, or any optimizer in PyTorch or TensorFlow to get my policy gradient. This is extremely scalable because you don't need to solve any MPC problem in real time. It doesn't have course of dimensionality because we are not enumerating any active constraints, and it doesn't require expensive label data. This is all done in self-supervision. So it kind of resembles reinforcement learning in sense of policy gradient. The main difference is, as I already alluded, that our critic is fully based. It's basically differentiable MPC lag loss function that requires known costs and system dynamics that are fully differentiable. And this enables the policy gradient. In reinforcement learning, in actor critic method, all of these would need to be learned from data by neural representation. And that what is makes it quite expensive. Because you need to approximate this critic. In DPC, you have the critic from MPC. And how does it compare to model-predictive control, where you can really think DPC is just a neural solver to obtain approximate solutions to parametric model-predictive control problem. In structural sense, when you look at implicit MPC in its dense form, also called single shooting formulation, in linear system models, your state trajectories are uniquely defined by the initial conditions with these matrix powers over here, and this lower trigonal matrix, also called dense formulation, that computes the effect of the control trajectories on state trajectories, right? This nice recursion of the state space model. Well, if you look at structurally at DPC, what we are doing, we are unrolling the closed loop computational graph. So you can really think of it as a single shooting approach to this MPC problem, but done in a batch. Instead of single instance, like it is done in online MPC, where every time you change the initial conditions or different reference trajectories, you need to recompute this problem to get the new control trajectories. Here, we are training this over distribution of initial conditions, over distribution of reference trajectories to parameterize the feedback policy in neural network. Okay, so it's a approximate explicit MPC utilizing single shooting factorization of the closed loop dynamics and using automatic differentiation to compute the sensitivities for the policy gradients. Any questions here? Good. So I will summarize all of these four methodologies that I see to be just different instances of broader toolkit of scientific machine learning. And this vision of unification is being materialized in Neuromancer scientific machine learning library that I'm developing for already quite some time. I think it's 5 years now, where we have user-friendly examples how to train physics-informed neural nets, learning to optimize for constraint optimization problems, how to learn a nonlinear system identification model with neural differential equations and other methods like deep Koopman approach, and learning to control with differential-algebraic control. So these are really served with few abstractions built on top of PyTorch. So the library backend is built in PyTorch, and for controls and operation research people comes with familiar user interface that we are used in algebraic modeling languages like Casadi or CVXPy or PyOMO, where we write our mathematical formulation of the optimization problems, we construct the variable objects, and then we write them in few lines of code as these expressions. And we provide this API that is really inspired by CVXPy or PyOMO on top of PyTorch. What is the difference here? Well, in PyOMO, you write your problem formulation, and now the PyOMO is mapping this problem formulation to solver-specific form. whether you're using interpretability or whether you're using Gurobi or quadproc, like it will require a certain inner form. Here, instead of parsing the optimization problem into solver-specific formulation, we are embedding it with these neural solvers and construct a computational graph, or so-called neural architecture, scientific machine learning architecture, that has 4 major components. It has the data set, it has the neural approximator, the mapping, it has domain-aware layer, objectives and constraints, and then it aggregates everything in physically informed loss function. And this has been project co-developed with my colleagues at the Pacific Northwest National Laboratory that contributed substantially to its success and broader adoption, not only in the national lab, but more and more in academic settings. So where are we applying it in terms of the energy systems application? So I spent a lot of time going over methodologies, but now I want to come back to applied setting. Well, I have been working on building controls for over a decade, and Erkan has also been working on this area. So this is application that goes back to our time with Lieve Helsum in Belgium, where we have been interested in developing high fidelity models and model predictive control strategies for residential and commercial buildings. The problem with MPC for buildings is not that we don't know the physics. We know the physics, but obtaining these models is very, very expensive. Getting the high fidelity digital twin in Modelica can take months of time. And then formulating MPC problems with these high fidelity models is computationally expensive and potentially leading to numerical issues, because we are dealing with differential algebraic equations. You can have algebraic loops, and you can have stiff system dynamics because you have slow dynamics and fast dynamics on heat transfer in buildings and HVACs. So things get complicated very, very fast when you want to do everything model-based. So my idea was, okay, let's apply a control theoretic approach. Let's get surrogate models. Let's get simplified representation of the system dynamics, and then solve model predictive control problems. But in traditional MPC, you are kind of limited in what type of system ID models you can obtain. So the idea here is to use the scientific machine learning surrogates, physically informed model. In this case, we used constrained state space models, where each of the components represent a different part of the building, whether it was the thermal envelope, whether it was HVAC system. And because we knew the physical properties like dissipativity of our heat transfer model, we could embed these constraints as a structural domain-aware constraints that provide us with control theoretic model that was suitable for control, at the same time expressive for learning. And because now it's machine learning model, it's implemented in PyTorch, we can use differential predictive control to form the closed loop to get the explicit control policy that is now easier to deploy and faster to evaluate compared to nonlinear model predictive control. And typically we are getting orders of magnitude faster inference time. That's really one of the reasons why you want to have these approximate control policies as opposed to solving the full problem in real time. Another example, we applied this methodology basically in exactly the same structure, was in power systems in dynamics aware economic dispatch problem, where we have a power system network, and we have desired set of loads from the grid, and we want to match the load by optimizing the dispatch schedule of our generators. So this is, again, hard optimal control problem that requires solving the physics, which is, again, given by differential algebraic equations. So in this case, we approximated with deep Koopman model, and so this offline by training these approximate control policies. And when compared to full nonlinear model predictive control with differential algebraic equation solvers, we get 5 orders of magnitude acceleration at the inference time. Of course, we are getting approximate solutions. So now we need to be careful, like what type of constraints are you satisfying in a soft way. Those needs to be guaranteed either by post-processing or by verification. So I'm looking at the time, and I don't think I have a time to go over some of the recent advances. How can we learn surrogates for differential algebraic equations with hard equality constraints? Or how can you even differentiate through mixed integer programs by approximating the gradients of rounding operations? So I will skip those, and I will try to conclude. But if you are interested in some of these topics, yeah, please reach out to me. I'll be happy to share the slides or papers. So what I wanted to take you away from this talk today, that there are a lot of emerging methods that are called physics-informed neural networks, or learning to optimize, learning to model neural ordinary differential equations, or learning to control, that I see as instances of the same family of methods that we can call scientific machine learning, that integrate deep learning, constraint optimizations, physics-based modeling based on differential equations, and control theoretic principles. So what we are really having now is not new theories, but it's new engineering infrastructure built on top of automatic differentiation that allows us to interconnect and fuse those different techniques that have been used by controls, operation research, and applied math communities for decades in one coherent algorithmic and theoretical framework. So this presents enormous challenges for modeling, optimization, and control of complex systems at scale. There are, of course, challenges that are still open in this domain, specifically how do you deal with discontinuities, with mixed integer problems, because we have these complex and deep computational graphs. Their sensitivities, the gradients can get ill conditioned. So how do we deal with that? How do we deal with the trade-off of offline pre-training and online adaptation and the cost of guarantees? I haven't talked about that today much, but yeah, there is always a trade-off between hard constraints and soft constraints and how much compute you pay for that. So I will stop here, so we still have some time for questions at the end. But if you are interested in these methods, again, go and look at Neuromancer library. We have a lot of open source code that you can just grab and use for your applications or modify to a new system and start using it today. So thank you very much for staying here.